In this chapter, we're going to start taking a look at the idea of a number of different extensions of direct proof, and then we're also going to start taking a look at a second method of proof called indirect proof. And so in this section, we're going to be taking a look at the quotient remainder theorem. We're also going to be taking a look at being able to prove using a direct proof called division into cases. We're going to start looking at the div and mod functions. And based on those, we're going to be taking a look at floor and ceiling, and then also proofs involving floor and ceiling. And then finally, we're going to take a look at indirect proof in this section. And there's two methods of indirect proof that we're going to be looking at: contradiction and contraposition. So those are the big ideas that we're going to be looking at for this section. So let's start out with our quotient remainder theorem. The quotient remainder theorem suggests that any integer can be written in this form, dqr. So if we have an integer n, dqr, where r is going to be less than d, but r is greater than or equal to 0. And so why would we want to do that? Well, we'll see a few proofs as to why that might be useful for us later. But for right now, let's just go ahead and apply the quotient remainder theorem. So let's just take each of these different numbers and see if we can write them using the quotient remainder theorem. So we have n is equal to 31, and we're going to define d as 5. All right, so if we're writing this, we're going to have that 31 is equal to 5q plus r. And we have to write it such that r is between 0 and 5, since we define d to be 5 here. And so we're going to come up with a value of q, and we know that 31 could certainly be written as 5 times 5 plus 6. But that doesn't make sense according to quotient remainder theorem, because 6 clearly does not fall within that compound inequality. So that's what we're looking for. We're looking for a specific pairing of q and r. And so I think a better pairing, in fact, the only one that works, is going to be when q is equal to 6 and r is equal to 1. And that's going to give us our 31. And again, r fits into that domain, the compound inequality. We could do it again. And for letter B, we could suggest that 109 is going to be equal to 13q plus r. And we know that 0 is less than or equal to r is less than 13, since we define d to be 13 in this case. And so in this instance, we could just say something to the effect of 109 is going to be equal to 13 times. Now, if we try 8, we know 13 times 8 is going to give us 104. So that seems like it's going to work really nicely. And so we can say in this case that q is going to be 8 and r is going to be 5. And that fits the domain from 0 to 13. All right. Now, for a negative number, it's still possible. So we can say negative 79 for letter C is going to be equal to 8 times q plus r. Now, r is going to be between 0 and 8. And so one of the most common errors that usually happens is that a student might do something like this. Negative 79 is equal to 8 times 10 plus negative 1, right? And unfortunately, that doesn't work because r can't be negative. Okay, r has to always be greater than or equal to 0. In this case, sorry, negative 10. So if we want to try to do this, or say, for instance, they might say negative 8 times negative 11, and then plus 9 or something like that, where they go over and they go back or something like that. So unfortunately, that's not the correct pairing, because that would be outside the domain. All right, so here's how we're going to have to do this. We're going to have to go just a little bit under. So we're going to use negative 10. So that's going to give us negative 80 and then plus 1. All right, so q can certainly be negative. In fact, q can be any number in the integers. and then r is going to be 1. And this works out for us because r is in the domain. That's what our quotient remainder theorem says. As an extension of this, let's use the quotient remainder theorem as defined by n equals dq plus r to list all possible cases that satisfy the given conditions. All right, and this is going to be important later when we start doing proofs involving the quotient remainder theorem. So for letter A, we have n is going to be equal to dq plus r, but we know that d is 3. Right? And so what does that mean? That means that r has to be between 0 and 3, inclusive of 0 but exclusive of 3. So all the possible cases would be 3q plus 0 or 3q, 3q plus 1, which is 3q plus 1, and then finally 3q plus 2. All right, and we can't have 3. All right, so in reality, it's going to be 0, 1, and 2 are the only cases. Okay. And then the same thing could occur for d equals 5. So we're going to have n equals 5q plus r, and r is going to be between 0 and 5 and exclusive of 5. So this is going to be 5q plus 0, or just 5q. And then we could just go all the way up from there. So n would be 5q plus 1, n would be 5q plus 2, n equals 5q plus 3, and then n equals 5q plus 4. So hopefully that makes sense as to how to go through and define the quotient remainder theorem, and then use it to build the different cases that would satisfy. Now, the last thing we're going to do in this video is we're going to do a basic proof of division into cases. And division into cases is used when you don't necessarily have a definition, but you can formulate definitions by breaking into cases. And you probably remember that every integer is either even or odd. You know that every number is either positive, negative, or 0. Or we could try to build one of the forms by the quotient remainder theorem. So we just said if we can prove all of these cases valid, then the entire statement would be true. All right, so basically it's exhaustion. You might remember that way back in section 3 that we were able to validate statements by exhaustion. So this is how we're going to do it. Division into cases is done by essentially the same method that we've been using, except we're just going to have more than one part to our direct proof. So we're going to define the variables like we're used to. We're going to write a conclusive statement. And then right here is the only difference in steps 2 and 3, where we're going to have to write out the different cases, and then we're going to have to prove the different cases. All right. So let's go ahead and show a basic example of this. For all x in the integers, x squared minus x plus 3 is an odd number. All right, so before we even think about this, let's think of the different possibility. So the cases could be even and odd. And that's easy because remember, we have a definition for even and we have a definition for odd. So that might be the easiest way to approach it. In fact, that's probably the best way I would suggest it at first, because that only gives you 2 cases to work with. And it doesn't matter that this is odd, the outcome's odd. So the antecedent just says integers. All right, so here's our proof. Let's start by saying, let's let x be an element of the integers. And of course, such that x is arbitrary but particular. And we can say that since x is an integer, all integers are either even or odd. So those are our 2 cases. So we've gone through, we've defined the variables, and then we've written out the cases. All right. So now we're going to prove each case. Okay? So we're going to have basically a subheading. all right? And for computer science people, subroutine or a function. So case one, and case one is going to be, let's do the easier case where x is odd, okay? So x is in z odd. So let's let, or I'm sorry, even. So let's let x be an element of z even. And by definition of even, we can say that x is going to be equal to 2n, where n is an element of the integers. And now what we can do is we can go through and we can use substitution on this and try to prove that it's going to be odd. Okay, so by substitution, we can say that x squared minus x plus 3 is going to be equal to 2n squared minus 2n plus 3. Right? And now's where we're going to do all of our computations. Right? So we're going to FOIL this out, or we're going to multiply it out. So this is 4n squared minus 2n plus 3. And remember, you can just say exponent rules. And remember that trick to be able to verify that a polynomial or even a structure might be odd. We're going to use the trick where we're just going to break up 3 by computation and just say that 3 is 2 plus 1. So that's by computation. We can now factor out a 2 from the first 3 terms only. So that's going to be 2n squared minus n plus 1 plus 1. Okay, and that's by factoring. And remember our integer closure. So right here, we can just call that p. Okay, so we're going to say that's equal to 2p plus 1, where p is an element of the integers. Okay, and that's by closure. Right. And so hence, we can say that x squared minus x plus 3 is equal to 2p plus 1, which is odd by definition of odd. All right, so we're going to hold it here because we've actually verified case 1. We're not going to close it out, but at least we've suggested that it is odd. So now we're going to go ahead and verify case 2. And case 2 is going to be where x is an element of z odd. All right, so this is a little bit tougher because of the algebra, not too terrible. So we're going to say, let's let x be an element of z odd. And by definition of odd, we're going to say that x is equal to 2n plus 1, where n is an element of the integers. We're going to do our substitution. So by substitution, x squared minus x plus 3 is now going to become quantity 2n plus 1 squared minus quantity 2n plus 1 plus 3. Now we're going to go ahead and do some multiplication. Right? So this is going to be equal to, now remember, this is a FOIL problem. And this becomes 2n plus 1 times 2n plus 1. So this is going to be equal to 4n squared plus 2n plus 2n plus 1. Right? So that's from this part right here. We're going to distribute the negative. Right? And that's just by multiplication. So I'll just put it right here. Right? Now we can combine like terms. So we have a positive 2n and a negative 2n. We have a positive 1 and a negative 1. So we just combine our like terms. We get 4n squared plus 2n plus 3. Okay, and that's just by polynomial addition. And now we're back to the same structure that we saw before, where we can go ahead and use that trick, where we can just break off the 3 into 2 and 1. Okay, and that's by computation. We can factor out from this term, and this term. Excuse me. And let me just reverse these just to make it a little bit easier. So that way it's just a little bit nicer. So that way we don't have to kind of guess around as to where I factor. So this would be 2 times 2n squared plus n plus 1 plus 1. Okay, and that's by factoring. And just like we saw in the previous case, this can just be written as p. Right? So this is going to be equal to 2p plus 1. We know that p is an integer, and that's by closure. Right? And that's the definition of odd. Right? So we can say, hence, x squared minus x plus 3 is equal to 2p plus 1, which is odd by definition of odd. All right. Now here's where we're almost done with this. Okay, so we've proven both cases. So if we go back up, case 2 is valid, case 1 is valid. They both equal 2p plus 1. So it's undeniable that since every integer is either even or odd, and we were able to show that it's true for both the even and odd cases, then we've actually proven it by exhaustion. All right, so we can say, therefore, by case 1 and case 2, x squared minus x plus 3 is an element of z odd for all x in the integers. All right, and that's kind of our closing statement because we've proven it for both. All right, so as you can see, division into cases is a little bit longer than what we're used to, not more difficult, just a little bit longer. So in the next video, we're going to take a look at 2 more examples of being able to verify some sort of statement by using division into cases.